Hi everyone. In this video, we are going to discuss on tutorial 23 and the topic is heat transfer. Okay, question number 1. A good conductor of electricity is a good conductor of heat. However, the reverse statement is not true. So explain the above sentences. Okay, the answer is a good conductor of electricity has many free electrons which allow heat transfer via collision of electrons. Hence, a good conductor of electricity is a good conductor of heat. But a good conductor of heat which transfers heat using only lattice conduction is not a good conductor of electricity, as there are no free electrons to conduct electricity. Okay, so now we go to question 2. A rectangular slab is made of two different materials, R and S. The thermal conductivities of materials R and S are 2 beta and 3 beta respectively. So in the steady state, surfaces K and L have temperatures theta 1 and theta 2 respectively. Okay, where theta 1 is larger than theta 2. Okay, calculate the fraction of the total heat through the slab that passes through material S. Okay, so the material S is at the bottom of material R. So the surface K is here and surface L is at the back. Okay, so the given question, in the question given thermal conductivity of R 2 beta and thermal conductivity of S is 3 beta. Okay, so the surface K, let's say the temperature here is theta 1, okay, given theta 1, and then at another surface L is theta 2. So theta 1 is larger than theta 2, so that means the heat flow is from surface K to surface L. Okay, so the questions one fraction. So fraction for material S, okay, heat for material S. So that's mean QS over total of heat. Okay, Q is heat. So heat for S and divided by total heat. Okay, total heat. So to find total heat, so we use Furier's law. Okay, so in time t seconds, so let's say the heat flow is Q. So for the using Furier's law, okay, the rate of heat flow, which is Q over T, is equals to the total of QR over T plus QS over T. So the Furier's law equation or formula is dq by dt equals to negative Ka d theta by dx. Okay, so at steady state, the Ka d theta by dx is a constant value. So we calculate separately. We determine separately, okay, the Qs and QR, right? For S and for R. Okay, for R, using the formula, so QR over T is negative 2 beta. This is KR. We substitute into the equation here, Furier's law formula. So A, cross-sectional area, times d theta by dx. Okay, so for material S, QS over T equals to, so the K is negative T beta. Okay, for material S, cross-sectional area A, they have same cross-sectional area, then d theta by dx. Okay, so the thickness of material R and material S is the same. Okay, so we substitute these two equations into here with the total of Q over T will be negative 2 beta A d theta by dx plus negative 3 beta A d theta by dx, and we get negative 5 beta A d theta dx. Okay, so this is the total of the heat flow. So we substitute into here. The time taken can be cancelled out, so we get QS over Q. Okay, so we substitute for QS from equation 2. So for equation 2 is for material S. So the QS over T is 3 negative beta A d theta dx divided by total Q is negative 5 beta A d theta dx. So we simplify this, we get 3 over 5. So this is the answer, the fraction. The fraction of the total heat through the slab that passes through material S. So that's mean QS over Q is 3 over 5. So that's the answer. Okay, now we go to question 3. Explain why the thermal conductivity of zinc decreases slightly as its temperature increases. Okay, so the answer, we use the Purest law. Again, the Purest law. So as the temperature increases, we know that the vibrations of the atoms increase. So from the animation here, okay, the vibration of the atoms increase. Okay, as a result, there are more collision between the free electrons and zinc atoms. Okay, this the mean time between collision will decrease. So therefore, the mean speed of the free electrons decreases, which is kinetic energy. Because of kinetic energy decreases, that's mean the mean speed of the free electrons decreases. Okay, hence the thermal conductivity of zinc decreases slightly. Then from the Purest law, we can see clearer here the relationship between thermal conductivity and the temperature change here. Okay, so when the temperature change increases, the thermal conductivity decreases. So that's why the thermal conductivity of zinc decreases slightly as its temperature increases. Okay, so that's the answer for question 3. So next we go to question 4. A rod of uniform cross section has a temperature gradient negative 1.2 Kelvin per meter. So the thermal conductivity of the rod is 30 watt per meter per Kelvin. Find the rate of heat flow through the rod and state one assumption made for the calculation in A. So the diameter is given in the diagram, which is 50 centimeter. So from this diameter, we can find cross-sectional area. So from the Purest law, we can use area and then the temperature gradient and the thermal conductivity K. Okay, so diameter here, we can use for Purest law, which is dq by dt equals to negative ka d theta by dx. Okay, so the area we can use pi r squared, and then r is d squared over 4. So we substitute the diameter into the equation here, convert to meter, and we get 0.196 meters squared. So we substitute into the Purest law equation. K is 30 and then d theta by dx is negative 1.2 Kelvin per meter. So the answer is 7.06 joule per second. So this is the rate of heat flow through the rod. Okay, next question B. State one assumption made for the calculation in A. So we assume that no heat escapes through the curved surface of the rod, but only through its cross section. Okay, because actually we need to put a insulator around the rod, so that no heat loss through surrounding. So we assume that no heat escape through the curved surface of the rod. Okay, now we go to question 5. Okay, the temperature below shows an unlike rod with the two ends maintains at constant temperature, theta 1 and theta 2 respectively. The two end pieces are made of a material of lower conductivity than the rod. Okay, sketch a graph of temperature against distance between the two ends. So theta 1 degree Celsius at one end, then the other end theta 2 degree Celsius. Okay, the rod is unlike. Okay, it is a unlike rod. So from Fourier's law again, dq by dt equals to negative ka d theta by dx. So we have two n pieces are made of material of lower conductivity than the rod. So that's mean the two n pieces here has different k, different k from the rod, unlike rod here. Okay, so that's mean we know that from the relationship here, uh, the thermal conductivity decreases when the temperature increases. Okay, so when we sketch a graph, temperature against distance, as asked by the question, so we will get the graph decreasing, the temperature, okay, decreasing with distance increases. Okay, so the temperature gradient, okay, from here, uh, for K, lower K, so the temperature gradient will be higher. Right? So you can see that these 2 point, that means shows the two ends here, which made of material of lower conductivity, lower K. So lower K, high gradient, okay, high temperature gradient. So these two ends, make sure you draw with same gradient, okay, same gradient. And the temperature gradient for the middle rod here, unlike rod here, is lower gradient, okay, with lower gradient. Okay, so that's the answer. Okay, now we go to question 6. Question 6. The figure below shows a thin wire XY attached to two copper supports which are heated by an electric current flowing in the direction as shown. Okay, current flow from X to Y. Okay, sketch a graph of the variation of the temperature along temperature theta along the wire with the distance X measured from X. So the distance measured from here. Okay, so question A first, question A. So the graph for temperature again distance, okay, will looks like this. Okay, why? So the temperature is given depends on the resistance of the wire, so because it's a current flowing, okay, current flowing, so from V equals to IR, so the current the current depends on the resistance of the wire. So we can see that the wire has different thickness, so depends resistance here depends on the cross section area of the copper, copper, both wire made of copper. Okay, so through electric current, the temperature we can see through electric current flow. So when resistance depends on the cross section area, so that's mean the thinner copper wire, okay, will give the higher resistance, okay, higher resistance, or oppositely, uh, for thicker copper will give you lower resistance. So resistance, lower resistance mean lower temperature, okay, lower temperature. So lower resistance mean lower temperature. Okay, so when we plot the graph, so it looks like this. So let's say we name the temperature at for thicker copper is theta 1, theta 3, and the middle here thinner copper theta 2. So theta 1 is equals to theta 3 because they have same thickness, and we label at the two ends here theta 1, theta 3, and for theta 2 is a thinner wire, so that's mean the temperature at theta 2 will be higher than theta 1 and theta 2. So you get a curve like this. Now we go to question 6. The figure, not still question 6, but for question B. So the question B, given current 1.5 ampere flow in the wire XY, and resistance of the wire is 3 ohm, and the cross-sectional area is 4 times 10 to the power of negative 4 meters squared. The temperature gradient d theta by dx is negative 10 degrees Celsius per meter. So we are going to find the thermal conductivity K of the wire. So we can use Furer's law, but from Furer's law dq by dt equals to negative Ka d theta by dx, but we don't know dq by dt, but we can find this using power. So power equals to I squared R. This is the power dissipated in the wire here. So the current given and also the resistance also given, so we can get the power dissipated in the wire or power loss, which is equals to the negative Ka d theta by dx. Okay, so we rearrange the equation here. We get K equals to I squared R over negative A d theta by dx. So substitute all the values into the equation and we get the answer 1700 watt per meter per Kelvin. Okay, so that's the thermal conductivity of the wire. Okay, next we go to question 7. The figure below shows a well-legged copper rod with a cross-sectional area of y centimeter squared and the length of 35.0 centimeter. Okay, when a steady state is okay, the temperature at the ends of the rod are maintained at 150 degrees Celsius and 45 degrees Celsius respectively. So that's mean the heat flow from high temperature to low temperature. When steady state is attained, the rate of heat flow is 34.2 watt. So area given, length, and the temperature 1 and temperature 2. The steady state given, so heat flow 30 dq by dt 34.2 watt. So calculate the temperature gradient along the wire, along the rod. So we can use Furer's law. So d theta by dx. Okay, we can use straight away d theta by dx. Okay, formula because given temperature given already. So d theta is 45 minus 150. Temperature change, so final minus lower. Final is 45 degrees. The heat flow from high temperature to low temperature. So 45 minus 150 divided by the length 35 centimeter, convert to meter. So you get temperature gradient negative 300 degrees Celsius per meter. So that's question A. Answer. Then for question B, find the value of Y. So to find the value of Y, so Y is a cross-sectional area. So we can use the Furer's law, dq by dt equals to negative Ka d theta by dx. So d theta by dx from A we can substitute into here, and dq by dt is given, and the K for copper is not given, but it's okay, you can get it in the textbook. So it's 330. So Y is what we're going to find. So the answer Y is 3 times 10 to the power of negative 4 meters squared. Okay, for the last question, find the temperature at 10 centimeter from the colder end. So that's mean from the colder end is 45 degrees here. Okay, 45 degrees. From here, 10 centimeter from the colder end. So we use temperature gradient d theta by dx because it is steady state. So any point you choose, 2 points, the temperature gradient will be the same. Okay, negative 300 degrees Celsius per meter. So that's mean somewhere theta here minus 150 degrees. Okay, measured from here. So theta will be lower or less than 150 degrees Celsius. So theta minus 150 divided by distance is 35 minus 10 because from lower end, okay, from colder end. So 35 minus 10 times 10 to the power negative 2 convert to meter. So it's equals to negative 300. So you get the temperature is 75 degrees Celsius. Okay, so that's the answer. Okay, and question 8. The figure below shows a perfectly lagged composite conductor which consists of two different metals rods P and Q. Okay, so the table shows below shows the details of P and Q. Okay, given length and then cross-sectional area and conductivity of material P and Q respectively. So at steady state, compare the temperature gradient for P and Q respectively, and the temperature difference between the ends for each of the rods P and Q. Okay, they are joined together here. Okay, so dx length, dx length for wire P and Q. So this is A and this is K. So at steady state, dq by dt. Okay, we are going to find temperature gradient. So d theta by dx, we can use Fourier's law. Okay, so they have same because they join end to end of the rod. So their at steady state, the rate of heat flow will be the same. So for P is negative Kp A d theta by dx. Okay, temperature gradient for P, and for Q negative Kq A d theta by dx for Q. So we substitute the uh, thermal conductivity for P, which is 2K, and then for thermal conductivity for material Q is negative 5K. So temperature gradient will be the same, d theta by dx. Ka temperature gradient for different material is not the same, so temperature gradients for P equals to temperature gradients for Q, so remain the same. Cancel Ka, so we get the answer, temperature gradient P equals to 5/2 temperature gradients for Q. Okay, so the question asked to compare. Okay, so we get the answer here. So temperature gradient for P is equals to 5/2 temperature gradients of Q. Okay, now we go to question B. Temperature difference between, compare the temperature difference between the ends for each of the rods P and Q. Okay, temperature difference. Okay, that's mean d theta. Okay, d theta. So theta 2 minus theta 1 over distance. Then theta 3 minus theta 2 over distance, because temperature difference. Okay, so we know that theta 2 less than theta 1 and theta 3 less than theta 2. Okay, because the heat flow from theta 1 to theta 3, high temperature to lower temperature. So theta 1 minus theta 2 over theta 2 minus theta 3. So here we get, we take the higher temperature minus lower temperature is okay, because either when we use the temperature, final temperature minus initial temperature, also we can cancel out the negative and we get the same answer. Okay, so from Fourier's law, we substitute the value for each of the heat flow through P and through Q. Okay, for heat flow through P, okay, dq by dt P equals to negative 2Ka. So theta 1 minus theta 2. Okay, we take positive, so that's mean here we can put theta 1 minus theta 2 because we didn't put negative there. So we take higher minus lower. Okay, then the distance will be 2/3L given in the table here. Okay, so for Q we do the same. So the distance for the length for Q is L. Okay, L, and the temperature is theta 2 minus theta 3. Okay, because we didn't put negative at the end here, at the initial here. Okay, so now these two equation, we can use ratio, equation 1 over equation 2. Okay, and then we can cancel the dq by dt because at steady state they are the same. And then L also cancel out, and we rearrange the equation to get theta 1 minus theta 2 over theta 2 minus theta 3. So we get KA cancel out, L cancel out. So what we get? We get 5 over 3. The 2 also cancel out. So that's mean we get 5 over 3. Okay. So that's the answer. Okay. And question 9. Two metal rods A and B of identical cross-sectional area have lengths 90 centimeter and 40 centimeter. Okay, and respectively, the thermal conductivities of A and B are Ka and Kb respectively. The composite rod is perfectly insulated as shown at the following page. So on the end of A, one end of A is maintained at 84 degrees Celsius and the opposite end of B is maintained at 12 degrees Celsius. So this means the heat flow is from uh, right to the left to the right, left to the right. Okay, at the steady state, the temperature at the junction is 26 degrees Celsius. Okay, find the value of uh, thermal conductivity A over thermal conductivity B. Okay, cross-sectional area given, distance A, distance B, temperature, thermal conductivity A, thermal conductivity B. Okay, so temperature at B and temperature at A and a temperature at the middle. Okay, so from the Furier's law, okay, so we substitute for A first, dq by dt equals to K for A, okay, cross-sectional area A, they have the same cross-sectional area. Then 84 minus 26, so we can use higher minus lower without the negative in front. Okay, no negative there. So that's mean 84 minus 26. But if we got negative in front, so you must use 26 minus 84. So be careful with the equation you choose. Okay, they have, both of them has same rate of heat flow, so you equate them. For B will be 26 minus 12 over distance, convert to meter, 0.4 meter. Okay, so now ratio Ka to B will be 35 over 580 over 9. Okay, so you simplify this, you get 63 over 116. Okay, so that's the answer for question 9. Okay, so that's all for tutorial 23 and bye-bye.